Welcome to the course on computer design of electrical machines. We will have a lecture 32 today on design of reluctance mode machines part 2. We will start the outline of the today lecture starting with the introduction, the analytical method for computation of motor flux linkage, the design consideration for reluctance motors, then determination of design parameter, stator, rotor and winding parameters, performance calculation of design reluctance motor, mechanical and thermal consideration of reluctance motor, followed by exercise and numerical problems and references like. So, coming to the introduction, the requirement for finding the performance characteristic of reluctance motor is to generate the relationship between flux linkage versus rotor position as a function of machine phase current, and a procedure for analytically deriving the machine characteristic given the motor dimension and excitation condition along with the number of turns per phase. In this reluctance motor, the aligning position corresponds to the center of stator and rotor pole coinciding, and aligning position with the midpoint of interpolar rotor gap facing the stator pole, and it is possible to calculate the flux linkages for the aligning position analytically due to the fact that the leakage flux is negligible in the aligning position, and it is not possible to calculate the accurate flux linkage for the unaligning position because of the leakage path are not known, as well as the air gap is large. So, coming to an analytical method for motor flux linkage computation. The analytical flux linkage calculation, the relationship of motor output variables to motor dimensions, the number of poles, number of turns per phase, excitation current and current conduction angle is not explained. Hence, a change in one or many of the rotor and control variables require an entire finite element analysis computation, which is either in 2 or 3 dimensions, and each set of finite element computation takes considerable amount of time. To save time and analyze the effect of design parameters on motor performance, analytical model is required, and the final design emerging from this analytical approach can be analyzed with finite element modeling to improve the accuracy of performance prediction. And flux maps are usually derived based on experience of the designer and can be fine-tuned with the finite element analysis tool to improve the accuracy of the flux path. And typically the flow of this analytical flux calculation is typically with the given in flow chart here. From starting, we assume the initial value of the stator pole flux density BAP, and then calculate the find the stator flux per pole pi SP, calculate the flux in path 1 for various machine segments and area cross section of the various segment encountered by flux tube 1, then evaluate the flux density in the various segments, and from BH curve of laminated material find the H corresponding to B of that particular segment, compute the length of flux path in each segment L, and compute MF of each segment by taking the product of its H and L, derive the magnetic equivalent circuit and write the ampere circuit equation, circuital equation, and compute the error F H delta F, F minus delta HL, and the test whether it is within the error excitation, and if delta is less than greater than FC, then we can say you say no, then we of course increase or decrease the flux density from which we started for typically in stator pole, or if yes, then we go to, if it is less, then find the final value of VSP, compute reluctances, and hence the inductance contributed by flux tube 1. Likewise, the compute inductance contributed by various flux tubes, because there are number of positions at which the inductance will be varying, and some of the inductance contributed by the flux tube to obtain the inductance of the winding. Now, typically taking a flux linkage at a line position, as you can see in the diagram, with the notation of 1 and 7 as how the rotor and stator pole are aligned. So, the derivation of the inductance is much simpler for the stator and rotor pole aligning position than the aligning position, and the flux lines about 90 to 98% pass the air gap between the stator and rotor, and there is a small flux due to leakage between adjacent poles. So, coming to typically flux path 1 consists of majority of the flux and is mutual flux connecting the stator and rotor. So, flux path 7 has leakage flux only when connecting the excited poles with the adjacent pole and carries only a small flux. And this typical example for flux path 1 and 7 given here in the diagram with the typically under aligned condition. So magnetic equivalent circuit for the aligned position consists of here the reluctance RSY1 on typically on the from both side, and then you have a MFF followed by 2 times RSPL, then 2 times RGL1, then 2 times RPL1, and then of course in the two parallel yokes MMF. So you can just understand it says a reluctance of different parts of magnetic as well as including the air gap. So there are typically 5 parts. I mean, you can call it here of magnetic circuit similar to like other machine. And when we go finally, typically a magnetic flux path aligned for path 7 with the MF F7 and flux consisting of 5 7 which have a reluctance of RSY and SP, the pole as well as the yoke, and typically the air gap RG7 like. So now you can just see how the flux linkage at aligned position consists of for the air gap. We can call it LG1 is LG, and you can calculate what is the area AG1, that is BS DL D by 2L plus BR in bracket D by 2 minus LG into L divided by 2. And similarly for that is for all these calculations for flux path 1 for aligned position, and then stator pole LSP1 equal to HS, that is the height of the virtually the pole. So an area is ASP equal to BS DL D by 2L, and rotor pole it is LRP1 equal to HR, that is height equal to height of the rotor. So and the area is ARP1 equal to BR in bracket D by 2 minus LG into L, and back iron is LRY1, that is the yoke of rotor. So that is pi by 2 in bracket D by 4 minus LG minus HR plus DS by 2, and area corresponding to ARY1 equal to in bracket D by 2 minus LG minus HR into L, and the stake back current we can call it the stator yoke, that's LSY1, the length is pi by 2 in bracket D plus HS plus HSY, and area HS ASY1 equal to BSY into L. So these are the calculation for path length. I mean path length in the sense length of magnetic circuit in different parts, and cross section area corresponding to this flux path line 1. Now because here the total air gap is gone changing, so now we have a similarly length and area for the section of flux path 7 in the aligned position. So for the air gap we can say LG7 equal to 3HS by 4 into pi by 2, and area is corresponding to AG7 equal to 3HS by 4 into L. Similarly for stator pole LSP7 equal to 1 by 2 3HS by 4 plus BSY by 2, and ASP7 equal to half in bracket 3HS by 4 into L. And similarly by stator back iron LSY7 equal to approximately LSP7, and the area is ASY7 equal to BSY into L. So now applying the Ampere's circuitous law, the MF calculated for flux path 1 are summed as SH FC equal to 2 in bracket HSP1 plus LS1 plus HG1 into LG1 plus HRP1 into LRP1 and plus HRY1 plus LR1 plus SY1 into LSY1. So these all 5 parts are accounted here, and from the calculated and applied MF, the error in the MF is found delta F equal to F minus FC equal to TPH into I minus FC, and the flux in the path flux path 1 is found now phi A equal to TPH into I, that is the MF divided by 2 in bracket 2 RSP1 plus RG1 plus 2 RP1 in bracket plus RY1 by 2 plus RY as ISY by 2. So that's give the flux into the magnetic path 1. Now coming to typically, and the path 1 flux contribute to an inductance equivalent to inductance, that is LA1 equal to TPH into phi upon I. And similarly for flux leakage flux path 7, the length of an area of the cross section of various parts in the flux path are FC equal to in bracket HSP7 plus you can call it LSP7 plus HG7 LG into LG7 plus HSY7 into LSY7 in whole as a bracket, and MF error for this calculator is derived delta F equal to 3 by 4 TPH into I in minus FC, and then the flux path is derived as phi 7A equal to 3 by 4 TPH into I divided by RSP7 plus RG7 plus RSY7, and the inductance due to the flux 4 flux path in path 7 as LA7 equal to 4 in bracket 3 by 4 TPH I divided by I, or equal to 3 TPH phi 7A divided by IA, and total allying inductance is calculated LA equal to LA1 plus LA7. So now coming to the flux linkage calculation at allying position, as you can see here, allying position we have here underlying rotor pole corresponding to different parts 1, 2, 3, 4, 5 and 6 and 7, as you can see here. So 7 path for the analytical calculation of allying position of this 8 by 6 8 pole on stator and 6 pole on rotor 4 phase reluctance motor. So flux linkage as an allying position is more completed. So starting from flux linkage in subcategorized into 7 parts as path 1, 2, 3, 1 and up to 7 for inductance calculation at an allying position, and the leakage and flunging are more at the underlying position as compared to the allying position, and the flux and the path length and the area is used for the reluctance measurement in the each part of the motor in different parts. Now coming to typically flux path at allying position for flux path 1 at allying position, as you can see in the diagram, the position flux path is air gap stator pole, stator back iron and rotor pole back iron. So actually passes through 4 parts, and calculation for you can call it flux linkage and length of the flux path in air gap Lg1 equal to d by 2 minus Lg minus Hr, and where Lg is the air gap during alignment and Hr is the rotor pole height, and area flux path in the air gap is Ag1 equal to Asp1 plus Ar1 by 2 equal to Bs dl upon 16 plus phi theta 3 in bracket d by 2 minus Lg minus Hr into L, where beta S is the stator pole arc and d is the bore diameter and L is the stack length. Now flux linkage at allying position path 1. So length of the flux path in rotor back iron is Lry equal to pi in bracket dsh by 4 plus d by 4 plus minus Lg by 2 minus Hr by 2, where dsh is the rotor shaft diameter, and area flux path of the rotor back iron is Ary1 equal to in bracket d by 2 minus Lg minus Hr minus dsh by 2 in bracket into L, where the quantity inside the parenthesis is the thickness of the rotor back iron. Now the length of the flux path in stator pole LSP1 equal to HS, and HS is the stator pole height, and area flux path in the stator pole ASP1 equal to pi d dl bs upon 8, and where d is the inner stator lamination diameter, bs is the stator pole arc, and L is the stator iron stack length. Now length of flux path in stator back iron LSY1 equal to pi in bracket d plus 2HS plus BSY by 2, and where BSY is the back iron of iron thickness. Area flux path of the stator back iron ASY1 equal to BSY into L, where the quantity inside the parenthesis is the thickness of the rotor back iron. So now from the final flux density in the various segments of flux path 1 and the magnetic field intensity, the reluctances are computed. The reluctance of the stator pole segment is RSP1 equal to LSP1 divided by SP1 mu 0 mu r equal to LSP1 divided by SP1 in bracket BSP1 divided by HSP1 equal to HSP1 LSP1 divided by BSP1 and ASP1. Now similarly, the reluctances of air gap, rotor iron and stator back iron are Rg1 equal to Lg1 divided by mu 0 Ag1, and Ry1 equal to HRy1 Lry1 divided by Bry1 Ary1, and Rsy1 equal to Hsy1 Lsy1 divided by Bsy1 and Asy1. So now the inductance contribution by flux path 1 at allying inductance is that Lu1, that we call it an allying position, Tph phi 1 divided by I equal to Tph into F1 divided by in bracket 2 as RSP1 plus 2 Rg1 plus Rsy1 plus Ry1 by 2 divided by total I equal to Tph square divided by in bracket 2 Rsp1 plus 2 Rg1 plus Rsy1 by 2 plus Ry1 by 2. So now coming to the flux linkage and allying position flux path 2 as shown in the diagram. For the flux path 2 at underlying position, the flux passes through air gap, stator pole, rotor pole, stator back iron and rotor back iron as shown in the figure. So flux linkage at underlying position in part 2, length of flux path in air gap is Lg2 equal to RBC into BC by pi by 3, and area flux path in air gap is Ag2 equal to ASP2 plus ARP2 by 2, and sp2 is the area of the your stator pole, and arp2 is the area of the rotor pole in part 2. Now length of the flux path in stator pole is LSP2 equal to HS, where HS is the stator pole height, and area of the flux path of stator pole is equal to SP2 equal to half in bracket beta S by 4 into D by 2 into L. D is the diameter of stator laminations, beta S is the stator pole arc, and L is the stator iron stack length. Now you can see now the length of the flux path in the rotor core is LPR2 equal to HR by 4. HR is the rotor pole arc, and area of the flux path in the core is ARP2 equal to HR by 4 into L. As you can see, all the reluctances connected here with the in part 2 F2. Now length of the flux path in the rotor iron LRY2 equal to LRY1. Area of the flux path in rotor back iron ARY2 equal to ARY1, and length of the flux path in the back iron LSY2 equal to LSY1, and area of the flux path of stator back iron is ASY2 equal to ASY1. The ampere circuit equation for flux path 2 is written from the magnetic circuit, that is F2 equal to in bracket 2 RSP2 plus RG2 plus RSP2 bracket close plus in bracket RY2 plus RSY2 divided by multiplied phi 2. So the your RMF is delta F equal to TPHI minus in bracket 2 RSP2 plus RG2 plus RSP2 bracket, and then typically plus R by 2 plus RS by 2 into phi 2, where so from the flux tube to the for we can have a formula for phi 2 equal to TPH into I divided by 2 in bracket RSP2 RY2 RG2 plus RP2 plus RSY and plus RY2, and the inductance contributed to the flux path 2 is underlying as underlying condition is LU2 equal to 2 PH into phi 2 upon I. Now coming to the flux linkage at a line underlying position 3, the flux path as you can see in the diagram, the flux path 3 and underlying position is flux passes through air gap, stator pole, rotor pole, stator back iron and rotor back iron. And now length of the flux path in air gap is Lg3 equal to RBC, that is BC into pi by 3 as you can see in diagram, and area flux path in the air gap is Ag3 equal to ASP3 plus ARP3 by 2. ASP3 the area polar stator pole and ARP3 the area of rotor pole in path 3. Now length of flux path in the stator pole LSP3 equal to HS, and HS is the stator pole height, and area of the path of stator pole flux path of the stator pole ASP3 equal to 3 by 32 in bracket beta S into D by 2 into L, where D is the inner stator lamination diameter, beta S is the stator pole arc, and L is the stator iron stack length. So length of the flux path in rotor pole LRP3 equal to 3HR by 4. HR is the rotor pole height, and area of flux path of the rotor pole, that is ARP3 equal to HR by 4 into L. So length of flux path in the rotor back iron LRY3 equal to LRI1, and area of flux path in rotor back iron is area ARY3 equal to AR1, and the length of flux path in back iron LSY3 equal to LSY1, and area of flux path of stator back iron ASY3 equal to ASY1. Now the flux tube 3 at underlying condition for inductance, that is phi 3 equal to TPH into I divided by 2 in bracket RSP3 plus RG3 plus RSP3 plus RSY3 plus RY3, and the inductance for total flux path is LU3 equal to TPH into 2 pi 3 divided by I, and that is 2 PH pi 3 upon I. Now the flux linkage at the underlying position 4 as you can see in the diagram. So the for flux path 4 at underlying position, the flux passes through air gap, stator pole, rotor pole, back iron, rotor back iron, and the length of the flux path in air gap is Lg4 equal to BC, and area of the flux path in the air gap is Ag4 equal to AS4 plus AR4 divided by 2. AS4 is the area of the stator pole, ARP4 is the area of rotor pole in path 4. And now length of flux path in stator pole is LSP4HS, HS is the stator pole height, and now the area of the flux path in stator pole is ASP4 equal to 1 by 32 beta S D by 2 into L plus HS by 16 into L, where D is the inner stator lamination diameter, and beta S is the stator pole arc, and L is the length of stator iron stack length. Now length of flux path in rotor pole is L RP4 equal to 7 HR by 8. HR is the height of rotor pole, and area of the flux path in rotor pole is ARP4 equal to HR by 4 into L. And now length of the flux path in back iron LR4 equal to LR1, and area of the flux path in rotor back iron is AR by 4 equal to AR1, and length of the flux path in stator back iron is LS4 equal to LS1, and area of flux path in stator back iron S4Y equal to S1. Now the flux for flux tube analyzing inductance is phi 4 equal to TPHI divided by 2 into bracket RS4 plus IG4 plus RSP4 plus SI4 plus RY4. The inductance contributed flux path 4 at a line condition is LU4 equal to 2pH into phi 4 upon I. And now coming to the flux linkage at unlying position flux path 5, as you can see in the diagram. So the flux path 5 at a lying position is the flux passes air gap, air stator pole, rotor pole, stator back iron, and rotor back iron portion, and length of flux both in air gap is Lg phi equal to half in bracket dB plus dC into phi theta 4, and area of flux path in the air gap is Ag phi equal to ASP 5 plus ARP 5 divided by 2, where ASP 5 is the area of the stator pole and ARP is the area of rotor pole in flux in path 5. Now length of the flux path in stator pole LSP 5 equal to HS, and HS is the stator pole height, and area of flux path of stator pole equal to ASP 5 3 by 4 HS by 4 into L, and is the inner diameter lamination diameter, beta S is the stator pole arc, and L is the length is the stator iron length stack length. Now length of flux path in rotor pole LRP 5 equal to HR. HR is the rotor pole height, and area of flux path in the rotor pole ARP 5 equal to in bracket d by 2 minus LG into BR by beta R by 8 into L. And now length of flux path in the rotor back iron LR by 5 equal to LR by 1, area of flux path in rotor back iron AR 5 to R1, and length of flux path in stator back iron LS by 5 equal to LS by 1, and area of flux path of stator back iron AS by 5 equal to S1. Now the flux for the flux tube 5 at the underlying position phi 5 equal to TPH into I divided by 2 in bracket RSP5 plus RSG1 RG5 plus RSRP5 in bracket RS5 plus RY5. Inductance contributed to flux path is underlying condition LU5 equal to 2 TPH Y5 divided by I. Now the flux linkage at unlying position for path 6, as you see in the diagram. So flux path 6 at unlying position, flux passes air gap stator pole and stator back iron, and length of the flux path in air gap Lg6 equal to OC into theta 2, and area flux path in air gap Ag6 equal to ASP6 plus ARP6 by 2, and ASP6 is the area of the stator pole and ARP6 is the area of rotor pole in path 6. Now length of flux path in stator pole LSP6 equal to 5 by 8 HS. HS is the stator pole height, and area of flux path of stator pole, that is ASP6 HS 4 into L. D is the inner stator lamination diameter, beta S is the stator pole arc, and L is the stator iron stack length. Now length of flux path in the stator back iron, that's LSY6 equal to in bracket d by 2 plus SS plus PSY by 4 bracket close in bracket another bracket 2 pi by PS minus 2 theta 1, where PS is the number of stator poles, and area of path in stator back iron S6 equal to S1, Y6 equal to SI1. Now the flux in flux path 6 equal to phi 6 equal to F6 divided by 2 SI6 plus RG6 plus RY6, that is 3 by 8 TPH IPH divided by 2 RSP6 plus RG6 plus RSY6. Now the inductance contributed to flux path 6 at aligning position LU6 equal to 4 in bracket 3 by 8 TPH phi 6 divided by I. Now the flux path for path 7 at aligning position, the flux passes through air gap, stator pole and stator back iron. The flux length of the flux path in air gap is Lg7HS by 4 into pi by 2. Area of flux path in air gap is Ag7 equal to ASP7, and ASP7 is the area of stator pole. Length of the flux path in stator pole equal to LSP7 HS by 4 plus BSY by 4, where HS is the stator pole height, and area of flux path in the stator pole equal to ASP7 equal to HS by 2 into L, where the T is the inner lamination diameter, beta S is the stator pole arc, and L is the stator iron stack length. Now length of flux path in the stator back iron, LS by 7 equal to HS by 4, and area of flux path in stator back iron, AS by 7 equal to AS by 1. So flux path, for flux path 7, the phi flux in path 7 is equal to phi 7, 1 by 4 TPH into I divided by RSB 7 plus RG7 plus RSY7. And you can see equivalent circuit how it looks like in a magnetic circuit for flux path 7. Now the inductance contributed flux path 7, LU7 equal to 4 TPH by 2 into phi 7 by I, or 2PH phi 7 by I. Now inductance, underlying inductance is obtained as a sum of all inductance contributed by flux path 7 flux path as given here, LU equal to J equal to 1 to 7 and LUJ. Now coming to design consideration for reluctance motors. Now preliminary steps for design is design of SRM start with the selection of frame size, stator outer diameter D0, stack length L, and shaft outside diameter DSH. So from the IEC standard based on the required power and torque rating of the machine, in practice 3 mm of frame size is left for mounting purpose, and initial stack length can be chosen as distance between the frame mounting hole. Now coming to selection of secondary data, selection of phase voltage of the winding is chosen based on the power rating, then air gap length, selection of steel type, pH curve characteristic of the material used in stator and rotor laminations has to be examined, and it is assumed that the stator pole flux density is equal to the knee point of the BH curve while designing the machine. Now coming to the choice of phases, starting capability, single phase machines have starting problem and require permanent intermediate position to serve this purpose. So in direction capability, number of phases decide when the machine can run in one or two directions. For example, single phase or two phase machine are designed to run in only one direction. Their reliability, this increases with the increase in phase numbers because of failure of one phase kept the machine running with the remaining healthy phases. The reliability is highly relevant in critical applications such as defense mission actuators in nuclear power plant, aircraft generator, and icebreaker for research missions. Now coming to the cost, as the number of phases increases, the corresponding converter phase units and their drive, logic, power supply, and control units increase, and this increases the cost and size of the machine. Now coming to power density of the machine increases with the number of phase numbers, and efficient high speed operation. Efficiency is enhanced by reducing the core loss at high speed by decreasing the number of stator phases and lowering the number of phase switching per revolution. So this is the reason why the 3-phase machines are preferred over the 4-phase in an aircraft starter generator SRM because of its high speed operation and the need for to keep the size is smaller, which requires a great reduction in the losses to maintain thermal robustness. These practical issues limit the SRM configuration to 6x4 and 8x6 in most of the applications. Now coming to why higher phase numbers, the reluctance motors should have the more than 2 phases before successful operation because the value of absolute overlap is required to be at least 1 to make the motor capable of producing torque at all the rotor position. The absolute overlap ratio is the ratio between the absolute torque zone, that is pi upon nr, to the stroke angle, 2 pi upon stroke divided by revolution, that is 2 pi divided by m into nr, where nr is the number of rotor poles. So this ratio should be m by 2, where m is the number of phases. To make it this ratio 1, so m has to be 2. The number of strokes can be increased with more phases without increasing the number of poles. So torque dips are removed with the more phases. And typical example is here when you have a 3-phase, you have some torque ripple, and then 4-phase you have a less torque ripple, and 5-phase you have very small torque ripple because of overlapping concept like. So now coming to choice of stator and rotor pole combination. So configuration available are 2x2, 4x2, 3x2, 4x4, 6x2, 6x4, 6x6, 8x8, 8x6, 8, 10x8, 12x8, and 12x10, and many more. So it is preferred to have non-integral value of the stator and rotor pole ratio. The limiting factors in the pole selections are number of converter switches, cost of associated gear drive, logic, power supply, and control requirement in terms of rise and fall times of phase current. Now stator phase frequency is given Fs equal to Wr divided by 2 pi into Pr Hertz. As the rotor pole increases, the stator frequency increases, resulting in a higher core loss. Increase in switching frequency results in commutation torque ripples, which can be filtered easily and provides quiet operation. The applications such as fans or pumps and vehicle propulsion, higher number of poles may not be necessary as they can withstand higher commutation torque ripple. Based on guidelines, the industrial design include mostly 6 by 8, 8 by 6, 12 by 8 and 12 by 10 combination. Now, why less rotor pole than the stator? SRM may have more rotor pole than the stator, which leads to smaller stroke angle and lower torque ripple. However, it suffers from the following drawback: lower inductance ratio, higher core losses, increased VA rating of the controller, decrease in specific output. So therefore, SRMs are preferred with large number of stator poles with advantage like high inductance ratio, reduced copper loss, shorter frame size, decrease in underlying inductance. So now coming to choices of pole arc, the stator and pole angle selection form a crucial part of the design process. So there are many guidelines to be followed during the selection process. The standard design normally has a stator pole arc angle smaller than the rotor pole arc angle, and the constraints on the value of pole arc angles are briefly described here. The rotor pole arc is greater than the stator pole angle, that is beta r greater than beta s. So stator pole arc should be greater than the stroke angle for starting the machine. So beta s should be greater than E, and the angle between the corners of the adjacent pole must be greater than the stator pole arc. So 2 pi upon r should be greater than beta plus beta r. Now selection of pole arc, as you can see in the diagram, here is the only feasible region. I mean, if you really talk about stator pole arc to rotor pole arc, I mean, in this feasible region only we design the typically your reluctance model. Now coming to determination of design parameters. So the output equation relates to bore diameter, length, speed, and magnetic and electric loadings to the output of the machine. And the output equation of SRM will significantly different from that of the conventional machine. The flux linkage voltage relationship for a flat topped phase current I is obtained by V equal to d lambda upon dt equal to lambda a minus lambda u divided by lambda u, or LA S minus LU into I divided by T, where LUS is the laying inductance, LU is the underlying inductance, V is the applied voltage, T is the time taken for the rotor to move from underlying to aligned position. So that time can be expressed in terms of stator pole arc and rotary speed. So tau T equal to beta s upon omega rm. So beta s is the stator pole arc in radian and omega m is the rotor speed in radian per second. So defining the sigma s equal to LAS divided by LAU, and sigma u equal to LA, you can call it U divided by LU. So well, LAU is the aligned and but unsaturated inductance, as you can see in the diagrams, like how really it can be modeled in different parts of this typical inductance or flux linkage versus stator current characteristic. So now the applied voltage appears V equal to omega m upon beta s into LA s into I in bracket 1 minus 1 upon sigma s sigma u, and in terms of flux density and machine dimension, LAS into I equal to phi into TPH equal to B into ASB into TPH, or equal to B into D into L into beta s into BH by 2, where phi is the aligned inductance, and typically your ASB is the area of stator pole, D is the bore diameter, L is the axial length of the stator pole, B is the stator pole, beta is the stator pole, B is the stator flux density aligned position, and TP is the number of turns per phase. So now we can call stator current may be obtained from the specific electrical loading AS, as AS equal to 2 pH IM by pi d, where M is the number of phases conducting simultaneously. And the power developed is PD equal to K into KD into V into IM. V and I are the peak phase value, KD is the duty per cycle and K is the efficiency. So KD equal to theta I into Q into PR by 360. Using the above definitions, the power developed by the machine is PD equal to A into PD into pi square upon 121 into bracket 1 minus 1 upon sigma s sigma d into B into A, AS into D square into L into NR. So conventional output equation of AC machine is given as PD equal to KE, KD, K1, K2, B, AS, D square L to Nr in watt. So total the torque and power output are proportional to the product of specific electric loading and magnetic loading and bore diameter, and K2 is the variable dependent on the operating point of the motor and is determined by the stator page current, magnetic characteristic of the core material, and the dimension of the motor line. So the developed output power is obtained from this output equation: PD equal to KE, KD, K1, K2, BS, D square and NR in watts, where K is the efficiency factor, KD is the duty cycle of phase, K1 pi square 120, K2 equal to 1 minus LAS divided by LU. LAS is aligning saturated inductance, LU is the unaligned inductance, B is the stator pole flux density, S is the specific electrical loading, D is the stator diameter, inner diameter, L is the length of the stack, and R is the speed of the shaft in RPM. Now this is coming to like a design equation. You can see all the dimensions here in terms of beta S, beta R, dr, and D, and tau R, YR, HR, G8, tau S, HS, and YS, and DS. So these are the different dimensions which you see in this machine of 6x4 3-phase machine. Now coming to selection of dimensions, so diameter and stack length, especially the length, stack length as the multiple of multiplied the bore diameter as L equal to K into D. Output power equation results as PD proportional to K2 into D cube. The ratio, the range K2 is given by 0.65 to 0.75. Now coming to diameter length, so value of B in a aligned position can be taken as the available maximum for core length. The specific loading in ampere conductor per meter is usually in the range of 25,000, S equal to between 20,000 to 90,000, and small machines have air gap of 0.15 to 0.25 millimeter. The integral horsepower machine may have air gap from 0.35 to 0.5 millimeter. So now coming to the for non-servo application, the range of K can be 0.25 to 0.7. For servo application, it is usually between 1 to 3. So now coming to number of turns, the conductor size chosen such that the available winding space is to be filled. For a specific electrical loading and bore diameter, it can be seen that the product TPH and I are the constant. It's constant, and the best value for those will satisfy the following: small current implying the large number of turns, and small value of resistance and inductance. The winding imply the smaller number of turns. Now coming to stator back calculation of stator back iron thickness. So stator back iron thickness is determined on the basis of maximum flux density in it and by the additional factor of vibration minimization to reduce the acoustic noise. The flux density stator back iron is approximately that of stator pole, and if Ws is the pole width given in terms of pole arc as Ws equal to D in sine of beta S by 2. Now due to the consideration of mechanical robustness and the minimization of vibration, it could have a value of range of your BSY equal to from WSP to 0.5 WSP, and it is equivalent to higher value of BSY than its minimum. So now coming to stator coil dimensions, the stator coil dimensions give its width WC and length SC, emerges from the area of cross section of the conductor AC driven by current density and the number of turns TPH. A stator coil area is given in terms of number of turns and area of cross section of conductors by SC WC equal to AC TPH by 2, and the maximum WC is obtained by taking stator board periphery and subtracting the motor pole arc and gap between the coil and dividing them by 2 PS coils as WC equal to pi D minus PS in bracket beta S into D by 2 plus WCS by 2 PS equal to pi D divided by 2 PS minus half in bracket D by 2 beta S plus WCS. And available coil height SC is determined as equal to AC into TPH upon 2 WC or equal to AC into TPH in bracket PS divided by pi D minus PS in bracket PD by 2 beta S plus WCS. Now coming to calculation of stator pole height, the minimum stator pole height is approximately equal to the coil height, but the coil height to be held in place, and for that a small space is required near the pole face. The coil sitting at the root of the pole is not usually tight fitting, and therefore some additional space is lost, which must be accounted to calculate the stator pole height. and considering all the factors and the need of a smaller length of the pole HS, the pole height in terms of the coil height SC is given by HS should be between SC and 1.4 SC. Now coming to outside dimensions of the stator laminations, the outside diameter of the stator laminations by adding it to pole height and back iron thickness, it is given DO equal to D plus 2 BSY plus 2 HS. Now coming to rotor back iron thickness, the rotor back iron thickness BRY is based on the structural integrity and operating flux density. So to be chosen from has to be account for the larger interpolar area gap to provide the higher ratio between the lying and unlying inductances, but at the same time it is desirable to have shorter rotor poles to generate minimum vibration in the rotor. So now based on these considerations, the rotor back iron thickness in terms of stator pole width is normally 0.5 to BRY varies from 0.5 WSP to 0.75 WSP. Now coming to rotor pole height, so given the bore diameter, the air gap length, rotor back iron thickness and the rotor shaft diameter, the rotor pole height is given as R equal to in bracket D minus 2LG minus DHS minus 2BRY by 2, where DHS is the rotor shaft diameter. Now stator stack length of the motor, the stack length of the L of the stator is summation of the length of end turns L and D and LS. So L total equal to 2 L and plus HS, as you can see here typically in the diagrams. Like now coming to winding design, conventionally in ASRM has considering coil wound on around the each stator pole. So there are different ways in which these coils can be connected together to create the phase winding. Now your slots and coil, the cross section of motor is as shown in the figure, and the wires are wound around the each stator pole, and thus there are two groups of wire belonging to two different phases in each slot, and wire wound around the stator pole make up a coil, and the coil can have a 1 turn, 2 turn and more turns. Now typical example here how it is the coil number of illustration of turns, 1 pole 2 pole coil and multi-turn coil. Now coming to wires and slot fill factor. So magnet wires is widely used in SRM winding and has two major components, the bare conductor and the insulation material. So only certain portion of the slot area can contain the wires called slot fill factor, and there are two slot fill factors, bare copper slot fill factor and wire slot fill factor. Bare copper slot fill factor is the ratio of bare copper area over the slot area. So FF copper equal to 2 N turn NSTR into pi DC square by 2 divided by AS equal to N turn and NSTR pi DC square by 2 AS, where DC is the diameter of the bare diameter and FF copper of 0.4 means that the 40% of the slot area is occupied by the bare conductor. Now the wire slot fill factor is the ratio of wire area over the slot area of the one slot. So F wire equal to 2 N turn NSTR pi dW square d by 2 square divided by S equal to N turn S NSTR into pi d square by 2S, where dW is the diameter of the wire with the insulation, and the dW is always greater than DC for the same wire gauge. Thus for the same slot with the same number of conductors, FF copper is always smaller than FF wire. Now a higher slot fill factor means that more wires are to be inserted into slot. However, it should be noted that the slot should have enough space available, and not only the conductor but also the insulation layer. Round conductor, the slot fill factor is selected between 35 to 50%. For hand wound coils, the slot fill factor varies from 35 to 40%. The lower fill factor enables the hand winding, and higher fill factor might require a special winding tool or an automated winding process. So now coil connection, each phase of a SRM has multiple coils. So for instance 12 by 8 SRM has a 3 phases and each phase has a 4 stator pole, thus 4 coils, and you can just see how the stator coil is the electrical schematic equivalence. And now you can see connected 4 coils for phase A, 4 series coils connected and electrical schematic. Here as in the diagram shown here the coils and how they are connected. Coil 1, 2, 3, 4, coil phase A1, coil of A phase, coil A1, A2, A3, A4, and similarly you can say how they really are having a current flow into the two, typically in the different parallel path. The connection is shown two coil in series and parallel. So the series and parallel connection of phase A, two series to parallel, and depending upon the voltage and current rating of the machine. Now coming to design verification and performance calculation of SRM. So now coming to design verification, design of an SRM using the output equation is to be verified from the flux linkage versus current characteristic for both the aligning and aligning position. The aligning flux linkage can be very accurate. The same cannot be said for the unaligned values. The analytical technique to calculate the unaligned inductance may have 50 to 100% error compared to actual value, thereby introducing a 10 to 15% prediction error in the motor output. So the analysis of the other characteristic of SRM, such as calculation of losses in the copper and in the iron by parasitic current and hysteresis, is important for the design verification. So enough data are available to estimate the efficiency and other parameters of SRM. So the control can be designed based on the SRM characteristic determined by analytical method or finite element method. Now typically current and current density. So two current waveform for low speed and high speed are shown in the figure. As you can see here, the blue for low speed and green for high speed. So current waveform are different and corresponding RMS value of current. So well, if the current waveform of one phase of SRM or the complete electrical cycle is represented by a function IT over the complete electrical cycle T1 to T2, the RMS value of the waveform is calculated as IRMS equal to 1 upon T2 minus T1 and varying integration from T1 to T2 IT square into dt. So if the RMS current of one coil is IRMS, then the resistance of the coil is IR coil. The copper loss for that coil can be estimated is P copper coil equal to IRMS square coil into R coil. Now copper or winding loss is accurate estimation of SRM copper losses at all the speed are complicated by the fact that the current waveform in the SRM is not sinusoidal. The current waveform is dependent on operating condition, particularly the excitation current, speed, and the switching strategy. And the current waveform can be approximated to a rectangular block. So with this assumption, it has been shown that the RMS current per phase is given by IRMS equal to IP upon under root Q, where IP is the peak value of current. So then copper losses for Q phase conducting at a time are generally given by PCU equal to Q IRMS square RS, and the resistance of a single phase can be computed in terms of the specific resistivity rho, mean turn length LM, and the area of the cross section of conductor AC. So RS equal to rho LM upon AC into NT. So well, mean turn length of the winding turn given by LM equal to 2L plus OWT plus 2 Di into sine beta S by 2. Now core losses. The core losses are generally calculated by Stevens relation P core equal to CH into B and F into B PM की power A plus B BM plus C into F square BM square. So CH and C are the coefficient of hysteresis and eddy current losses, and AB are the constant. The eddy current terms in terms of our equation can be written as P core equal to CH F B BM power 1 plus B BM plus CE1 into dB upon dt square, where CE1 equal to C upon 2 pi square. Find the coefficient CH and C and the constant AB from the loss curve using a curve fitting process. A flux waveform in different sections of the machine are plotted. Average value of B dB upon dt calculated for each section, and the loss per kg of the machine is obtained from the above core loss equation and multiply the obtained losses with the corresponding weight of the each section. Now coming to first the flux density waveform for stator. The flux density of other poles are identical but are phase shifted by theta s, that is the delay angle between the phases when the energizing the corresponding phase winding, and each phase current is conducting for the theta c conduction angle and falls to theta f fall angle during duration, and the flux density in the different parts of stator are shown in the figure. You can just see how the typically in your stator pole body the flux shown as a rectangular waveform, and then typically in B7 different parts, like you can say B7, B8, B9, B1, then B2 and the B3. You can see how really the 1, 2, 3, 4 all are shown in different parts here. So still flux density waveform for the 6 pi 4 reluctance motor with phase A excited, how the flux density pattern is there. Now similarly for the rotor, The rotor flux density waveform for the C/4 SRM when phase A excited. In different part again, it is also shown here. The different part 1, 2, 3, 4 with the beta. Now coming to mechanical consideration of the reluctance motor. Now typically for mechanical consideration, first is the material selection. When choosing a material, it is important to identify the critical property that determine its selection. So for instance, most of the property listed could be examined for laminated steel. However, the critical property evaluated when first selecting a lamination steel are generally gauge, plug density, loss density, and magnetic permeability. And the component like shaft, bearing, housing, and slot liners help hold the motor together under operation, while the lamination is key, wire coating, and the speculation govern the performance of the machine. Now, even though the structure of a SRM is relatively simple, a good design that considers practical manufacturing requires a broad expertise and experience across the various disciplines. So, during the design phase of a motor, a large number of parameters must be carefully considered and determined. The two major dimensions of the motor frame are the motor casing diameter and the motor casing axle length, which basically determine the physical volume of the motor. So there are number of other mounting types, for instance, wall mounted, ceiling mounted, pedestal mounted, face mounted, and flank mounted. The major dimensions of the horizontally foot mounted electric motor frame accounting to National Electrical Manufacturing Association NEMA and the International Electrotechnical Commission's IEC. The size of the motor frame depends mainly on the volume of the stator winding, the subassembly, and the type of enclosure, the method, and type of mounting. So now it is a mechanical considered typical dimensions for foot mounted electric motor frames. As you can see, the different distances of bearing 1 to 6 of different parts of this machine. And then you can see all the dimensions, the housing of 20/6 traction motor, layers of SRM with water jacket for the water cooling, as you can see typically in the photogram. The 3-phase 24/16 reluctance motor is hybrid electric powertrain design and optimization is a part of. So now coming to for material selection for stator and rotor. So the stator and rotor in SRM are typically made on non-rented soft magnetic electrical steel. So the property of the core material are subject to numerous factors including purification of steel, controlling of alloy elements, grain orientation, and the grain sizing. So since the stator and rotor cores of SRM can be exposed to higher frequencies, it is often desirable to use electrical steel and lower losses. Now, similar to other type of electrical machines, the stator and rotor in SRM are typically limited to reduce the eddy current losses. So various thickness are available from lamination manufacturer for different applications and type of the machine. The sample core material for reluctance motor here it is like carbon steel ATS 1000 series, then silicon steel AK steel M series are from there, then soft material Halogen AB, then high saturation alloy carpenter Hebno, then amorphous alloy Hitachi Metaglass, and then nanocrystal alloys like Hitachi Metal FC. Now coming to laminations and stacking of SRM. The lamination stacking is the next process for assemble the stator and rotor cores respectively, and laminations are stacked axially on a material with key to align the salient poles and the salient slots and poles. The riveting and bolting offer reliable and economical solution, therefore are most implemented. However, the pivotal heads may interfere with the end winding and the hole punches in the laminations may introduce local stress and concentration and flux concentration, and welding is the another economical and reliable method. Now, the typically here you can see lamination stacking of SRM. So another stacking method is the lamination interlocking. So interlocking process requires a complex and expensive die. Just as you can see here how the limited stack of stator and exterior rotor. So coming to now winding insulation. The insulation layers are necessary around the copper conductor to enable the contact between the wires and without causing any electrical short circuit. So mechanical strength of the insulation is also much lower than copper or steel. So therefore electrical insulation around the conductor is generally the limit for the lifetime of the stator winding, and these insulation material are usually made of armide permeable layered paper. Nomex is an example of insulation paper supplied by DuPont for slot insulation, and thickness of the slot insulation material ranges between 0.1 to 0.65 millimeter. And you can see how the winding insulation put on lamination cover of Reluctance machine prototype with the insulation, and coil insulation on the prototype 6 by 10, typically from ED laboratory of Illinois Institute of Technology, Chicago. Now coming to thermal consideration of the SRM. So typically temperature consideration, temperature rise in a reluctance machine is caused by power losses generated by different physical mechanisms, and losses in reluctance machine are typically classified as copper, iron, typically core, mechanical and axle losses. Copper loss results from Joule heating due to the resistivity of the conductor, and losses have two components, eddy current and hysteresis losses. Now coming to mechanical losses, in particular friction and voltage losses also contribute the major temperature rise. So starting from power input, we have first for distribution of the losses as a copper loss, then core loss, then axis loss, then mechanical loss, and then power output. So coming to first as a copper losses. Copper loss is the major loss component in all electrical machines. So DC component of phase resistance is found through the resistance equation, which is a function of conductor geometry. The effect of temperature on the copper loss model is accounted by calculating resistivity as a function of the temperature. Rho T equal to rho 0 in bracket L 1 plus alpha in bracket T minus T0, and where rho is the resistivity of initial temperature T0, alpha is the temperature coefficient, and T is the final temperature. And this is how the typical frequency impact the phase resistance of rectangular wires for the copper loss. So as resistance increases with the frequency for the overhang conductor portion and active portion of conductor. Now coming to iron loss. So iron loss is another major loss component in reluctance machine. So it is typically dominant when machine operates a higher frequency, for instance at a higher speed. A simple approach to include the core loss in thermal analysis is to consider two heat sources. One is the stator and another is the rotor. Coming to now mechanical losses. Mechanical losses in electrical machines consist of friction voltage losses. Friction losses are mainly caused by the bearings, and the resultant heat and the heat passing to ambient via bearing increases the local temperature, and this tends to degrade the lubricant and reduce the life of the bearing. Now a general expression for friction voltage losses for all machines is PFW equal to 2D square L N cube into 10 power minus 3 KF B into G into N 10 power minus 3. So D, L and G are the outer diameter of rotor and length and weight of the rotor respectively, and N is the rotational speed and RPM, and KFB is the friction loss coefficient. Now excess losses arise from the complex interaction between the external magnetic field and the atomic scale interaction in the steel. So core loss equation can be rewritten to include this anomalous or excess loss. So P core equal to P stress plus eddy current P excess. Now coming to cooling techniques. The cooling technology can be classified according to the mode of heat transfer: conduction, natural convection, forced convection, radiation, and evaporation cooling. And they can also be classified according to cooling field: water, air, oil, and phase change material. So selected cooling technology depends on cooling requirement for the machine and on which parts are being targeted for cooling, core, winding, and or unwinding. Now typically coming to cooling technique. Technique depending upon the cooling target. Here is like a cooling target for core, winding, and winding. Start with direct cooling, direct with the water jet or air or fan, or indirect is water jet or air fan. And for stator winding, cooling channels, heating material, and heat exchanger, and the end windings normally cool liquid jets, spray cooling, and potting material. Now typically you can see cooling, how it is a cooling technique, how the air, typically induced ventilation with internal fan. You can just see how the air flows through, from one end to the another end, typically in this machine through air gap. And then the induced ventilation with the external fan, cooling technique, and the cooling technique with the forced ventilation internal fan, how the cooling, air blows, then how the forced ventilation the external fans, and how the water jacket cooling, then how spray and water jacket cooling. So now coming to thermal modeling of a reluctance motor. The prediction of temperature distribution in electric motor using thermal modeling is the key to designing the thermal management scheme. So common methods for thermal analysis include the lump parameter thermal network, LPTN, pure finite element analysis, and computational fluid flow dynamics, CFD. The LPTN offers a quick method for determining the temperature distribution within the electrical machines and allow the user to rapidly determine the changes resulting from variation in the input parameter. Now you can see how the thermal modeling, major parts of heat flow in the machine. So coming from ambient, then goes to how typically housing, how the losses are there in different parts like air, through radiation and through conduction and through convection. So all three, you can call it the different symbols with different colors. Radiation goes with the red, and the conduction goes of course with the gray, and your convection flow is with the typically your blue dotted typically, and how with the heat with internal heat how the internal heat generation with the red, how the with no internal heat generation and other internal ventilation. So different parts about the heat generation as well as the conduct different heat dissipation or heat flow is there in the thermal modeling of SRM is accounted. Now typically layers of SRM for thermal modeling in radian. So you have a different layers starting for different colors. It is shown here starting from first layer of slot, second layer of rotor back iron, the third is gray with the rotor teeth, and fourth is air gap, fifth is the stator teeth, fifth layer winding, seventh is the stator back iron, and seventh is frame, and eighth is the your ambient temperature. And this is the example of LPTN for the electric machine with the motor gate. Typically how the fluid, you can say different colors, it is shown here, this thermal consideration or variation of time. Now coming to temperature consideration, with the operating time, how do you change with the temperature rise? For housing, typically hot spot, then stator surface, rotor surface, then winding, average winding temperature, the cool spot temperature, hot spot temperature. Temperature variation for the motor component of the SRM at 3000 RPM, peak torque with coolant inlet temperature set of 65 degrees Celsius and the ambient temperature set at 4 degrees Celsius typically. So now coming to exercise and numerical problems. So coming to first question, as exercise, the cross section area of a one coil is 0.079 square inch, the stack length is 1.89 inch, and the current density is 4567 ampere square inch. Find the temperature rise on one side of the stack. Take a row as a 678 into minus 6 ohm inch and K 9.8. So the rate of heat transfer from the coil is J square rho. Putting a value, it comes 14.1 watt per inch cube, and one side of copper loss is putting a value typically here 2.1 watt. So temperature gradient along with the coil is given here, dt upon dx equal to q upon k. Putting a value, it comes 2.7 degree per Celsius per inch. So since the heat can flow in both directions, the temperature gradient is only 1/2 of this value, and the temperature rise between the ends of the stack and center is given as, putting the value is 1.2 degrees Celsius. Now coming to question 2, design a SRM with the following data: power output 500 watt, speed 750, peak current 7, peak phase current 79 ampere, frame OD 190 mm, stack pole plug density 1.3 5 Tesla, specific electric loading 30,000 ampere conductor per meter, air gap length 0.2 mm, stack pole angle, stator pole arc angle 20 degree, rotor pole arc angle 33 degree. Output equation is P equal to K KD, K1 K2, B S D square L N R, and here considering the validity of 1, K2 equal to 0.7, K equal to 0.655, and K is 0.8, and bore diameter is given from this equation, cube under root cube P upon K KD K1 K2 B A N NS in millimeter, and putting value, it comes 81.7 millimeter, and length of stack L equal to KD, so it's come 53.5 millimeter, and stack stator yoke dimension BSY equal to D by 2 beta S, so it comes 44.26 millimeter, and the height of the stator pole HS equal to D by 2 minus BSY minus D by 2, putting value, it comes 39.89 millimeter, and rotor back iron thickness BRY equal to D by 2 minus LG to BR, putting value, it comes 16.32 millimeter, rotor pole height HR equal to D by 2 minus LG minus DSH by 2 minus BRY, putting value, it comes 10.33 millimeter. The area of stator pole ASP equal to D by 2 beta S, into L, it comes 762.91 millimeter square. Area of the rotor pole ARP equal to d by 2 minus Lg, and BR into L, that is 873.12 millimeter square. Now area of the air gap AG equal to ASP plus AL by 2, that is 818.015 millimeter square. Air gap flux BG equal to BSP SP by AG, that is putting value 1.26 Tesla. Magnetic field intensity in air gap H equal to VG upon mu0, putting value which comes here 1.10 to power 6 into ampere per meter for peak current. TPH equal to Hg into 2Lg upon IP, putting value it comes 45 tons per phase. And assuming a current density of 4 ampere per meter, the area of the conductor is calculated is equal to IP divided by J root Q. So it comes 1.125 millimeter square. So standard wire 18 can be used. It has area conductor of 1.17 millimeter square. Now question 3. Design SRM with following data: power 500 watt, speed 3000 rpm, peak current 6 ampere, frame OD 200 millimeter, stake pole flux density 0.51 Tesla, specific electric loading 15,000 per meter, air gap length 0.25 meter, state pole arc angle 20 degree, rotor pole arc angle 22.5 degree, and considering the duty done, K1 equal to 1, K2 equal to 0.667, K equal to 1, 0.5, K equal to 0.5, so form turns per phase and phase aligned inductance. So D form the formula, cube root of is all dimension power, that comes 77.85 millimeter. Length of stack L equal to KD, putting value 116.8 millimeter. Stack area, so bore diameter is calculated D cube root of this comes 77.85 millimeter. Length of stack L equal to KD, that's 116.8 millimeter. Stack pole area ASP can be written as ASP equal to D by 2 beta H into L, putting value it comes 1.587 10 to the power minus 3 meter square. And the flux in stator pole pi sp equal to VSP into SB is 2.38 milliweber. Area of the rotor pole ARP equal to D by 2 minus Lg into VR into L, that 1.773 into 10 to the power minus 3 meter square. Area of the air gap AG equal to SP plus ARP by 2, that is 1.68 into 10 to the power minus 3 meter square. The air gap flux density BG BSP SP by AG, so putting value 1.416 Tesla. Magnetic field intensity H equal to VG upon mu0, it comes your typically 1126817 ampere per meter. A magnetic circuit equation written as F equal to TPH IPH, that is 2 HGLG equal to 563.07380. And since the initially the peak current was assumed to IP equal to 12, the turns per phase calculated TPH F upon IPH, that comes 94 turns, allowing in seizure inductance and maximum current neglecting leakage is calculated and allowing equal to PH 5 upon IPH, that's 37.7 millihenry. Now coming to question 4. Find the phase allowing inductance cell NC ratio if the motor is operating at rated operation. So SRM with the following data: power 500 watt, speed 3000 rpm, peak current 6 ampere, frame OD 200, stator bore flux density 0.51 Tesla, specific electric loading by 15,000 ampere conductor per meter, air gap length 0.25 millimeter, stator pole arc 20 degree, rotor pole arc 22.5 degree. Considering here the duty ratio 1, K2 0.667, K1 1.5, K equal to 0.8. So rated torque T equal to form power into 60 to pi n, that is 1.59 Newton meter. Torque for peak current I is given T equal to half I square dl upon d theta. Putting value here, dl comes 30.86 millimeter. Underlying inductance L equal to LA minus dl, that comes 6.44 millimeter. And silency ratio of the machine LA upon LE equal to 5.8. Now coming to question 5. Determine the diameter and length of 6 by 4 inner stator, 10 kilowatt SRM, rated speed of the motor is 1500, length of the diameter is 1.8, magnetic loading and electrical loading is 1.6 and 30,000 ampere per meter square. Assume unity duty cycle and 90% efficiency of the motor. The output power is from this equation: P equal to K KD, K1 K2, B AS, D square LN. And considering the parameters like K equal to 0.9, KD equal to 1, K1 0.0823, K2 0.68, B 1.6 Tesla, AS 25,000 and RPM 1500. So now coming stack length L equal to 0.8 diameter. So diameter cube from the output equation comes equal to 111 millimeter and L comes typically 89 millimeter. Now question 6, a 3-phase SRM has a 6 stator pole, 4 rotor pole and 2 coils per phase on the opposite stator pole with 50 turns each. The overlap angle between stator and rotor pole is 12 and air gap is 0.4 millimeter. Stator bore diameter is 60 millimeter. Axial length of stator stack is 55 millimeter. Stator and rotor pole are 30 degree both, and the current of 10 ampere flows through the two coils in series. Neglect the fringing and leakage and saturation effect. Assume the lagging inductance 0. Calculate the magnetic flux density in the air gap between the active poles. Electromagnetic torque and angle of the rotation at which the torque is essentially constant if the current is constant. The solution is given all data, given 3-phase, Ns equal to 6, Nr equal to 4, Tps 2 into 50, 100, D equal to 60 mm, L 55 mm, Lg 0.5, Bs equal to Br, beta s equal to beta r 30 degree, L I equal to 10 ampere, and P equal to 50. So for calculating a magnetic field intensity is equal to 2 N P I upon Lg, so it comes 125,000 ampere. Air gap flux density Bg equal to mu0 Lg, it comes on 1.57. 1 Tesla. Area of pole arc Sp equal to beta d by 2L. So putting value it comes 0.00069 meter cube. Area gap per inch eta equal to mu0 Sp upon 2 Lg. So it comes putting value 1.086 into 10 power minus 6, and maximum inductance align L equal to Np square eta. So it comes 0.11 or 11 millihenry, and unaligned inductance the torque 0. The torque produces T half square L and putting value 1.296 Newton meter. And these are the references from which this is closed. Thank you.